we finished our introductions to differential equations. We find that thing has a lot of applications and also a lot of types. Ordinary differential equations, systems, partial differential equations with uncertainty, control problems, those kind of things. Okay. We will, of course, focus on the very starting point, the ordinary differential equation. Now let's see. Then we talk about how to solve it. That's 1.2. It's about first order. Then it's also about separable differential equations. Okay, so the first one we were talking about is what do you mean by a solution? We have something called general solution, which basically means if you have a derivative involved in the equation, eventually you want to find what y is. For this case, you have to take integrals because you have derivatives. Then when you take an integral, you generate a constant plus c. You do it for twice, you have two constant. So basically the order of derivative or order of the differential equation, which means the highest derivative, is going to equal to the number of constant in your final solutions. And because your solution looks like this, with a constant, which can be anything, we call it the general solution, which means a family of solutions, infinite many. This includes x squared plus 1, x squared plus 2, x squared plus whatever number. Okay, so that's a lot of solutions. From here, you can see with one constant here, it's basically a one-dimension vector space. Okay, so that's where linear algebra is going to come into play. Of course, you have infinite many, but we kind of see like this is like one because you only have one constant. Then the second thing we were talking about is what if I want a special solution, which means there's no constant. Then of course, what you are going to ask for is additional information, which we call the initial value. Okay. Then what you will see is you will see a differential equation paired with initial values, or let's call initial condition either way. Okay, we call this thing an initial value problem. Which is not just a differential equation, but also initial values. We usually call it IVP from now, initial value problem. Okay. Then when you solve it, what you need to do is, number one, solve the differential equation, get the general solution. Number two, use the initial value to get the value of the constant. So together, you get the final solution, but this time, you will not have any more constant. This will be a solution not to a differential equation, but to a initial value problem. Okay. From here, you can see this step here is really easy. You just plug in and figure out C. So all the hard part is going to be solving the differential equation. So from now on, every time we introduce a new problem, usually what we do is we go ahead and find the general solution. And then we stop there. Okay, because the rest is easy. In real life, of course, you want to get the initial condition and solve that thing to the end. But in our class, usually we stop here because that's where the hard part is. Okay. Now, of course, you can have it right away. What if you want to solve something like this, which include second derivative? Then, of course, you are looking for two initial conditions. The first one is your y0 or maybe y2, whatever. The second one is going to be about y prime. 0 equals 5, things like that. And the logic is quite simple. You take y prime prime, you do integration for once, you get y prime. You're going to have a constant here. And we're going to use y prime 0 to find what this c is. Now, when you have y prime, you take integration again, you got y with another constant d here. Then we're going to use this y0 to find what d is. So every time you do integration for once, you use one corresponding initial value, you get one constant. Okay? So now if you go back to physics, now you know what we should do when you do a projectile motion. A complete problem should look like this. Y prime prime equals negative g. Okay. Gravity, that's it. But then you need to tell me the initial displacement, 3, for example. The second one is going to be the initial velocity, which is 5. Okay, that will be a complete set of problem in physics. From here, you can see, wow, when you solve it, there's no more constant because these two is going to help you to find C and D. Okay. So later in real life or in our exams, make sure that you know what I'm looking for. Am I looking for a general solution for a differential equation, or am I looking for a specific solution for an initial value problem? Okay. They're almost the same in terms of difficulty. Cool. Now let's go ahead and try to solve something called separable differential equations. Let's start with the very simple one. We did this before, right? We have y prime equals 2y. We solved it. We know it's e to the 2t. The way we solve it is we try to guess. We have something, we take the derivative, it's basically itself, and then we kind of play with after we guess it, we find, wow, number one, there has to be a 2. Number 2, there is a constant, which makes sense. Of course, we don't want to do things in this way. We want to be able to solve it following some steps instead of guessing. Okay? So think about it. How are we supposed to solve things like this? If it's this one, we take the integration on both sides. We got y and x squared. Now, what's the difference with the current situation? Well, you can still do the same thing. 2y. But now you should really ask yourself one question, that is, something is missing, right? We actually need to put something called dx here. And we should put something like dx here. And then you find a change of variable actually changes everything, because there's no way I can integrate with respect to y, integrate 2y with respect to dx. This one is not going to give me 2y squared. Not the case. Make sense so far? Okay, that's where the thing is. Then let's think about how to solve it. What you really want is you want to integrate this one with respect to y. And you want to integrate the second thing with respect to something different. Oh, sorry, not y, dt. Because y is a function of t. Okay, so it kind of makes sense for me to put all the y on one side and all the t on the other side to separate the two variables. One is with y and the other one is purely with respect to t. And we don't mix them together, so we know on which side which differentiation integral we should take. If you see a t, do dt. If you see a y, do dy. Still okay here? Now let's try to see how do we do this. Okay, we have 2y. I want all the y to be on the other side, so we got y prime over y. I want everything else to be on the other side, so I got 2. Keep in mind, this is for t, this is for y. Okay. Now let's take the differentiation with respect to dt. I have 2t plus a c. Perfect. Okay, keep in mind you don't want y and t together because you don't know which one you want to take, dt or dy. Okay, so let's separate them. Good so far? Now question, what about this side? Everything is in terms of y. I really wish this is in terms of dy, not dt. Otherwise, I can't do a thing. Right? But do you see a dy here? Can you see this part actually give you dy? And then what you're really dealing with is just this. But now dt and y prime together give you dy. Sounds good? Once it's in terms of dy, what's the antiderivative of 1 over y? What's the antiderivative of 1 over x? It's the same thing. That's L and y. Technically this, but we know y is going to be positive. So, but either way, let's just do that. Then what is y? Let's ignore the bar because we're dealing with positive here. That's just going to be e to the 2t plus c, which is e to the 2t times e to the c. C is any constant, then e to the c is any constant. It doesn't hurt for us to replace it by just a constant, any random constant. In this way, we get the solution again, but this time not by guessing. We also know this is multiplication because it's actually plus on the exponents. Everything makes sense here? All right. This is called separable. Oh no. Let me write it down. Separable differential equations. In general, we have y prime equals to a function of t and y, and they can be any type of thing. Okay. But then somehow, if you can separate t and y to be one and another, this is called separable. Then what you can do is you can move everybody with y on one side, everybody with t on the other side. We separate them. Then we take the integration with respect to dt. Okay. Then this part is legit because it's a function of t and you're taking the integration with respect to t. Great. The left part is not legit. It's a function of y. You are taking the integral with respect to t, but then you notice y prime and dt basically give you dy. So this one becomes now can you do the right hand side? The answer is yes. I have a function of t when I finish. Can you do the integration on the left? The answer is yes. It's a function of y. Integrate with respect to y. Then I'm going to have something with respect to y when I finish. I'm just going to call it capital H plus a c. Then everything is doable from now. You already have y as a function of t. Sounds good? So 2 steps. Step 1, recognize it's separable. Step 2, once you realize that, separate. Then, of course, if it's not separable from the beginning, you cannot separate. So this only works for special cases. Make sense here? Questions before we move on to the exercise? All right, let's try some exercise. We finished the first one, which is the E. Now let's try some exercise. Okay, let's say 1. Okay. Y prime equals yt. Okay, number 1, I want to take the integration. Then I realize, okay, I wish this y is not here because I want everything with respect to t. Suddenly I realize this is the y part, this is the t part, and it's separable. Again, ignore this. Does it work? You can check. Y prime is e1/2 t squared c prime, which is c e1/2 t squared times 2 times, 1/2 times 2t, which is y times t. That is the differential equation. So this one is the answer. Sounds good? Let's try another one. Remember, this was the logistic growth. It has a k, it has an n. For simplicity, let's just assume k equals 1 and n equals 1. Of course, the same analogy works for any other number. We just want the thing to look clean. So let's solve this instead. But once you can do this, it's just a matter of time you can do the original one. Okay. Everything is in terms of y, so Right-hand side, super easy. The left-hand side, at least doable. We change this to dy. Y minus y. Now it's just a matter of, do you know how to do the integral? Does anybody know how to do it? Calculus 2. Okay. Number one, simple formula. This is not simple, so no formula. Okay. Integration by parts. Trigonometric integral. Trigonometric substitution. Partial fraction. And end of story. That's all we know. How to do this? Anyone? Integration by parts, trig sub, partial fraction, and u sub. Andrew.
It's been a while since
Yeah.
Type 2.
That's the spirit. That's not the right spirit, though. But that's the spirit everybody has, who still kind of feel like you just make a guess, right? Integration by parts, what you're looking for. You're looking for something times something. Like, what I'm looking for trig sub. And then x equal to sine, things like that, right? What are you looking for if you have partial fraction? And what do you do by that? It's a over x plus b over x minus 1. And does this one look like a partial fraction? Awesome. So let's go with that. Okay, cool. Yeah, I know it's been a while. It's actually not, not just you. It's for everybody. So it's time for you to catch up. Okay, it's quick. It's just this. And I am just going to skip. You figure out how to find a equals 1 and b equals 1. Okay, but this works. Now what's the solution for the first one? Ln y. What's the solution for the next one? It's ln 1 minus y minus. From now on, I'm just going to omit this absolute value because we usually know what we're dealing with. Okay. We're not done. I want y equals something, t. Then the question becomes how to solve for y. Now it has been an even longer while since we solved this. How do we do this again? How do you solve this? Take e and then ln cancel, right? The problem is you have two ln. I wish there is only one ln. Can you combine multiple ln's together by doing the log property? So ln, if you're minus y over 1 plus y, sorry, 1 minus, equals t plus c. Now it's safe. That's y over 1 minus y equals e to the t plus c, which is c times e to the t. If you change, replace e to the c to be c. And then y equals 1 minus y c e t y equals CET minus YCET, y 1 minus CET equals CET, and finally your y equals this. Take it back, it's plus. All right, that's the solution of y prime equals y times 1 minus y. Now remember, the original thing is y prime equals ky 1 minus y. I'm not going to do it, but you should go back and try to do it. With general k and general n, you should confuse yourself a little bit and then work through it. Then you will feel good. Okay, I will give you the answer. P0. Oh, y0 equals y0, because this is important. So I will put it here. N y0 e to the kt divided by n plus y0 e to the kt minus 1. I would say not a homework, but assignment. Practice this. You should get the answer here. Sounds good? I think this will be the right level to put in the exam. I would say this is the right level. It's not straightforward. It's not too complicated either. Okay, so make sure that you're comfortable with at least something like this. Okay, so that's how we do separable differential equations. The hard part is actually not anywhere other than number 1, recognize it's separable. Number 2, do the actual integral, because we have experienced this before. Integral can be really difficult to solve. Okay, but at least this is something you can do. Okay, I'm just going to keep moving on because this is not an elementary class anymore. So if you guys have questions, just stop me. Okay, so instead of saying like, I pause for half a minute, I'm waiting for questions. All right. What about this? Do you find it difficult to just divide y there because of the sign? You cannot simply just do this, which actually a lot of people will do, which is, of course, ridiculous. So can't do this. And actually, you will realize no matter how hard you try, the sign always stops you from doing that. Okay, then not separable. Try something else. For now, we basically give up. Later, you will have something else. Okay, so the key is to make sure that it's separable. Okay, some other small examples to just show you some, how to say, I won't say rare, but some tricky situations you need to be careful. Okay, the first one is this initial value problem, y prime equals y, and y0 equals 0. Okay, now our focus is not on how to solve it, but more about be careful. Okay, weird things can happen. I think everyone can do it. After you realize it's separable, t plus c, all right. 1 over y squared dy, all right. Negative 1 over y equals t plus c. Your y is negative 1 over t plus c. That's the solution. Okay, that's easy. But now, we do have an initial value problem. So we have to do one more thing to figure out what c is. Then 0 is negative 1 over 0 plus c, which is negative 1 over c equals 0. Do you see the problem? For what c this one is going to be 0? Nothing. No such c. Make sense so far? Okay, you did all the problem. You find if I plug in the initial value, it never happened. Such a waste. But what's your answer? Kendra.
Would it just be?
Oh, Sam, go ahead.
Would it just be no solution?
Totally reasonable. Why? Because I saw for a general solution, I find your differential equation and your initial condition cannot coexist. If I solve your differential equation, I got this, I find this one can never happen. Okay, therefore, there is no way I can find something that satisfies both at the same time. No solution. Make sense? Who does not agree? Who think there is a solution? And I can tell you that solution. Take a look. Can you think about something which is not even hard, something trivial that satisfies both conditions? Doug.
It might be overly simple, but could it be that y is equal to 0, just as the final equation?
Let's forget about your first comment. It may be overly simple. But second question, do you think it's a solution, y equal to 0? What's y prime? Does it equal to y? Yes.
Mm-hmm.
What is y0? Is it 0? Yes.
Yes.
So y equal to 0 clearly is a solution. Okay, so no solution totally works. But then you realize y equal to 0 can be a solution. So when you do things like that, be extremely careful. Where do you think this mistake happened in this process? Doug, can you think of why we missed this solution?
Well, as we work our way down through the integrals, if y was equal to 0, we'd be doing 0 squared for any of them. But
you divided y squared on the other side, did you?
Yeah.
Okay. In this case, we have a hint. Actually, the flaw happened here. When you divide y squared, you are already saying something. Y cannot be 0, right? Y is not 0. The moment you do that, you miss this. Okay. So from here, you can see anything that may happen in elementary algebra sense, it will happen here. Okay, don't divide by 0, factor them out, things like that. So be extremely careful. You may miss something. That naturally leads to another question. If there is a way that I can tell how many solutions am I going to get at the beginning, then there's no way I can miss any solution, because if I from the beginning I know there are 2 solutions and I only found 1, then I know there's another one. Make sense so far? Okay, so that is actually a big thing which we'll introduce later. That is existence of solution. And moreover, the uniqueness of solution. Is there a way that we can tell before we solve it how many solutions we're expecting? And then if we don't find them, we don't find all of them, we know we're missing something. Okay, that is something we can actually do. Good. That's the first one. The second one, actually, sorry, that's the fourth one. The fifth one. Y over 1 plus y squared. Again, you can rewatch the notes, so I'm just going to go really quick here. The algebra is really not interesting, so divide. I'm starting to skip steps. So far, so good. Of course, this is not enough. We want something as a function of t. So our job becomes solve for y from here. And check your library before this class, you realize we don't know how. Okay, so this is just a small example to remind you, we can have something called implicit form of solution, which means everything works just fine until you are trying to write y as clean as a function of t without quoting itself. Sometimes this is not doable. Okay. In that case, just keep your thing here. Even though this one looks, I won't even say ugly, but not ideal, you can still analyze the solution. You can plot it. You know, you can find the solutions at somewhere, plug in a t. You can also find the derivatives. So it's really not that bad. Finally, of course, a quick example, not even worth doing. It's just sometimes you have y prime equals secant square y. Okay. You try to do everything, you find cosine y square dy. Sometimes things like this is just difficult to solve. So sometimes you have impossible integrals. Y square, sorry, secant y square. Otherwise, it's doable. You can do half angle formula. Okay. In this case, It is separable, but the integral is hard. Okay, that's the limitation of this method. Either way, you are still doing integrations. Integration can screw everything up. Okay. Is everything clear for this section? We have one type of first order differential equation we can solve. It's basically taking the integral. And your job before you take the integral is try to make it clean. So y stay on one side, dy. T stay on the other side, dt. Sounds good? Okay, good. Separable is a really interesting concept. For this case, you separate y and t. Just go to mention a little bit. Later, you will have partial differential equations, which means you have ut and ux and maybe uy. These are partial derivatives. Okay. By then, you will have another thing which is called separable equations. By then, you just want to separate x on one side, y on the other side, so you can still do dx or dy. So there's really no restriction that you want to do dy or dt or dx or anything. As long as you make sure that everybody stay on the right side, you can apply this separable skills. Okay. You actually have seen this before in calculus 3. That is when you try to do double integral. Which we all know we do this assuming the other one is a constant, right? But actually is a clever way to do it. It's just like do the x separately and do the y separately, and there's no confusion. Why? Because they can be separated. This is the simplest case. They are not correlated. The difficult case will be when they're intertwined together and there's no way you can separate them. Okay. All right. Everything looks good so far? Let's try one more example. This time we have some applications. I'm going to give you 2 applications. The first one super easy. We're taking a parachute and do skydiving. The second one, which is exciting, we're going to do the Friedmann's equation, which tells you that our universe is expanding and it's expanding at a certain rate. We're going to solve both. Let's start with the small one. Okay, let's deal with skydiving before dealing with the universe. Well, when you do skydiving, it's quite simple. Let x be your height, which is a function of t. Okay. Then, this is going to be ma equals f. You just need to do the f here. So what is the force when you're doing a skydiving? Gravity. Of course. Okay, most people do this because they want to simplify the model. They say there's no air resistance. Then you know this is not skydiving. This is called free fall. You're doomed to die. Okay, so what do you mean by skydiving? Well, there is certainly air resistance. Okay, and how big is air resistance? This is something we can test on the ground. You just take a car and just drive it. Okay, then when people test it, they find it's proportional to the square of your velocity. The faster you drop, the bigger the air resistance. That makes sense. The second thing is interesting. It's not linear. That means the resistance you feel when you run 20 miles per hour is not just a double what you feel when you run 10 miles per hour when you double the speed. You actually make 4 times. Okay, so that's the beauty. That's why skydiving is safe. It's not even linear. It's faster than linear. And of course, when you have something like this, it's nothing but x prime square. Now it's settled. This is a differential equation, which involves only x. If you don't feel comfortable, you can change it to y. Now it looks better. Okay. Now we want to solve it. How do we do that? Well, it's actually not a question. We only have one way, separable. Is this one separable? Well, this is just constant, right? These are constant. So how about we just think about this? Well, clearly it's separable. Make sense so far? Okay. Are you scared? Because clearly this one is not first order. This one is second order. Before, this give you dt, dy. If you have a y prime dt, right? But this time you don't. You have y prime prime dt. Should we stop here, say impossible, or somehow we can still work through it? Think about it. If you're not happy, just let u equals y prime. Okay, then what you're really looking at is y prime prime dt, 1 minus u square, where u is just y prime, right? Okay. Now you just wish you have du here. What is du? Du is dy prime, which is the derivative of y prime, which is y prime prime times dt, which is happen to be just this. Okay, so this is 1, and you got the du you want. Okay. When you solve it, you will have something u equals t plus c, which is actually y prime equals t plus c. Then how do you find y? You just take the integration again, you find y. Sounds good? So that even though this one is not first order, it's not even linear, you can do it. I will stop here. I will give you 5 points. Next time, if at the beginning of the class next time, you are willing to share your solution by sharing the screen, you can pre-work it out on a piece of paper and walk us through it. Okay, I will give you 5 points for doing that. Okay, and clearly from here you can see it's doable because yeah, it's 1 over 1 minus u squared. Do you know how to do the derivative of that, integration of that? You better be, okay? Cool. That's all for today. Feel free to leave